Hello, in this video I'm going to continue looking at special relativity and tie up a couple of loose ends from the previous videos, because we've been looking at time dilation and length contraction and doing some calculations, but I hadn't derived the formulae that we were using. So that'll be the main thrust of this particular video, and I'll do a few other practice questions and a bit of evidence as well for time dilation. So let's kick off then with the time dilation formula. So set up a couple of frames of reference, because this is what we need in special relativity. We're transforming between different frames of reference. So on the left hand side here, this frame of reference, I call it frame F, with some X coordinate, Y coordinate, and I'm going to have a light source A, which is at rest inside this frame of reference. It's going to emit a pulse of light which will travel in the Y direction up to B, which will be a mirror that then reflects the light back to A. And the total time for the light to go from A to B and then back to A again, I'll say, is delta T. So that's our rest frame of reference for the light source. Then on the right hand side, I'll set up a moving frame of reference relative to the light source. So we've got a Y prime, we've got an X prime, frame of reference F prime, and I'll set the motion of this frame of reference off to the left in the X direction, so the negative X direction at velocity V. Now the reason I've put it in the left hand direction, I mean, it doesn't really matter, you could do it off to the right, but I just find it a bit easier drawing the picture when it's going to the left. So we've got the source will start at point X here, and the light will then travel up to the mirror at B. But by the time it's got to B, B would have moved to the right because this frame of reference has moved to the left. So in frame of reference F prime, it will appear that B is moving to the right. So B will be over here at point Y, and then it will reflect back. And by the time it returns to the source, it will be at point Z over here, which is going to be also off to the right. So we've got that path. I mean, if I'd put V moving in the positive X direction, we just would have had the X and Z spots in the opposite, flipped over in the opposite way. The direction of travel would have been going off to the left rather than going off to the right. So that's the setup for our two frames of reference. Let's add in a few distances here. So let's say the Y direction here for A to B is D, that Y distance. And I've put this distance parallel to the y-axis and the motion of the other frame parallel to the x-axis, so we don't have to worry about length contraction because the motion is perpendicular to that distance, so we're not going to get any contraction of that length. So this distance here from y down to the line that's connecting x and z, that is also going to be a distance d, that altitude on that triangle. Then we've got the distance from X to Z. So that will be, if this path has taken a time delta T prime, from X to Z is going to be V delta T prime. That's just our distance is velocity times time. So now let's underpin these pictures with some mathematics then. So on the left-hand frame, this is the easier one. Total distance travelled is 2d. And that is going to be equal to our velocity, our speed of light, multiplied by the delta t, multiplied by time. Velocity times time is distance. So that's fine. Right hand frame, well, our distance is xy plus yz. And that is going to be equal to speed of light, because remember, in special relativity, the speed of light is the same in all inertial frames. So the c isn't changing, regardless of the fact that we've got relative motion here between these frames, and we've got relative motion between the frame F prime and the source. We're still getting a measurement of c for that speed of light. Now, this is one of our fundamental postulates of special relativity, and that will be multiplied by delta t prime. So we need to get rid of this x, y, and yz, both of which are the same distance. We can see this in the the symmetry of this setup. The travel time on the way out is the same as the travel time on the way back. And then we just need to do a bit of Pythagoras in order to get rid of these. So we've got two lots of one of these hypotenuse arrows that I've drawn here, this path from x to y, is going to be the square root of d squared plus, and then we've got v delta t prime over 2, so half of the base of the triangle, all squared. And then square root that is going to be c delta t prime. So all we need to do now is do a bit of rearranging and combine these two equations, and we get our time dilation formula. So I'm going to continue with this one here on the right, square both sides, so we get 4d squared plus, and this 2 on the outside of the square root, when we square that, it's then going to cancel with this 2 here, so that's all going to go away. So we get v delta t prime all squared is equal to c delta t prime all squared. Now there's 2 things we can do here. We want to group together our delta t prime squareds. So let's put that on the right hand side of this. So we'll have a delta t prime squared multiplied by c squared minus v squared. And that just leaves the 4d squared on the left hand side. And we can get that from here. If we square this left hand equation, then we've got 4d squared. So we can say c delta t all squared. Right, next up, let's divide through by c squared. So we'll have delta t all squared is delta t prime all squared, and then we're going to have 1 minus v squared over c squared, which is what we wanted to see. This is this Lorentz factor that we've got in all of our calculations. And we want delta t prime to be the subject of this, so it's a pretty simple step from here. Delta t prime is going to be equal to delta t divided by the square root of 1 minus v squared over c squared. So let's just unpick what these delta t's and delta t primes are then. So delta t, this is the time between 2 events happening at the same point of space in this rest frame here, this frame of reference F. As in, we've got the event of the pulse of light leaving A, and we've got the event of the pulse of light returning to A. So we've got 2 events occurring in the same point of space. So the time between those, this delta t, is going to be our proper time. That is our t0. So that's good. And in this case, this is then the time between 2 events in another frame of reference. So this is just our t that we've been using. So this is then in exactly the same format, t equals t0 divided by the square root of 1 minus v squared over c squared. That's exactly the same format as we were using in the previous calculations. So it's a relatively simple derivation, that of the time dilation formula. And as I was saying, there is evidence for this. This is something that can quite easily be tested in the real world. And one of the first ways that people were getting evidence, actual experimental evidence for this time dilation, is they were looking at cosmic rays. And cosmic rays, so these are high energy particles that are coming in from space and, well, interacting with the upper atmosphere of the Earth. Mostly we're talking about protons. You'll get a few alpha particles, a few electrons, but mainly it's high energy protons. And these protons come in and, yeah, they can cause, well, ionization. They can, cause the creation of new particles and things like that. They're bringing a lot of energy into the upper atmosphere. And one thing that they can produce is muons. And muons are unstable. And they set off from the upper atmosphere and they head down to the Earth's surface close to the speed of light. And this then allows possibilities of getting some evidence for time dilation. So what they were doing is they'd get a mountain, they'd stick a muon detector at the top, and they'd put a muon detector at the bottom, and they'd then record the rate of arrival of muons at both detectors for a particular speed of muon. So say they were saying, right, we're looking for muons that are going at 99.4% of the speed of light. Let's detect how many, the rate of arrival at the top, rate of arrival at the bottom, and then do a few calculations. So let's put some numbers behind this then. So say they were saying we had these, the height of the mountain, the distance between these detectors, let's say it was 1,900 meters. I've taken this from an actual case of where they were doing this. This was the height of the mountain, or at least that distance between the detectors. So they had that, and they said, okay, what's our travel time then? So the travel time, so this is the time as measured on Earth, is then going to be our distance divided by our velocity. So 1900 divided by our 0.994, and then times the speed of light, our 3 times 10 to the 8. So that tells us that time measured on Earth is 6.37 microseconds. So that's how long a clock would measure the time for a muon to get from the top of the mountain to the bottom of the mountain. And that's if the clock is in the frame of reference of the Earth, the rest frame of the Earth. Now, the half-life at rest of a muon is 1.53 microseconds, so significantly less than the 6.37 microseconds. But when they were measuring the rate of arrival at the top and the rate of arrival at the bottom it was about 73% of the arrival rate at the top. Now we're getting about 4 half-lives here. So, well, one half-life should take us down to 50%, another one should be 25%, and so on. So to have 73%, clearly we've got a different time from the point of view of the muon. So we can now compare equations, because we can look at our half-life decay equation and say, right, this 73%, I'm going to have to squeeze this on, let's squeeze it down the bottom here. So this 0.73, this is our ratio of the initial rate of arrival, well, our final rate of arrival divided by our initial rate of arrival. So that's our e to the minus lambda t, if we go back to our radioactivity equation, our half-life equation. And we've got the half-life of the muon. So we can say, right, this is e to the minus natural log 2 divided by the half-life and then multiplied by some time. We can now solve this equation, this 0.73 equals e to the minus log 2 over the half-life, solve it for t. That will give us the time in the frame of reference of the muon. So, i.e. our proper time, the shortest time that can be measured from top to bottom of the mountain. So you put all of this in, and our t0 then comes out at being 0.69 microseconds. So you can see we've got a very big difference here. And this is less than the half-life, which is what you'd expect, because we haven't had half of them decay. We're getting 73% arrival. So the time as measured in the frame of reference of the muon is going to have to be less than the half-life. That's why we've got more than 50% still being detected at the bottom of the mountain. Now, if you take the ratio of these and we take that 6.37 divided by the 0.69, we're getting around about 9.2, something like that as a ratio. If we then look at our Lorentz factor, our 1 over the square root of 1 minus v squared over c squared, and you put in that value for v, then we're getting about 9.1. So more or less the same value. I mean, if you were taking exact measurements on all of this, you would get exactly the same value. But you can see how this is verifying the time dilation formula here in a, conceptually simple experiment. You can see how this is going to work quite happily, and using our knowledge of decay of these particles, our decay equation. So yeah, I think that's quite useful just to see how they're backing up these theories, this special relativity, in actual practical examples. Right, so let's push on then with length contraction. So I'll go over to the length contraction derivation. So we're going to have the same thing then with 2 frames of reference. So frame of reference, we'll have a rest frame, we'll have a moving frame. So we're going to have the same stuff, f and f prime. So our y prime, our x prime, our x, our y. We're going to have a source, A. We're going to have a mirror, at B. So we're setting off this light pulse again. It's going to go from A to B, back to A. That's going to take our time delta t. So that's all good. And then in the other frame of reference, which we're going to have moving again, so we'll set this off, moving off to the left at some speed v. So we've got our initial point x. When it then hits the mirror, so that will then be our point y, because things would have moved, and when it returns to the source, it will return at z, because everything's moving off to the right. Right, so, and that's going to happen in time delta t prime. So the same sort of setup that we've got here. So we're still going from A to B. This time, though, you'll see I've put the direction of motion of the light and the direction of motion of the frame of reference f prime in the same direction. Everything's moving in the x direction. So we're going to get some length contraction. So let's start with our rest frame then. So we've got our length here. Let's say this is going to be our proper length here, our proper length L0. So the time delta t is going to be 2 lots of L0, the total distance travelled, divided by the speed of light. So we've got it set up quite easily again for the rest frame of A. Then we want to go over to the moving frame. So we've got our distance from x to y, which is going to be longer than L0. So they're going to start off L0, well, they're going to start off L apart, x and y, because we've got the length contraction. So we can't say that's L0. So they start off L apart, and then that is going to extend by some amount v times, well, we'll have to say delta t prime 1, because we don't know how delta t prime is split up. We can't say that it's going to be the same amount of time from x to y as back from y to z. So I'll split up delta t prime into delta t1 prime and delta t2 prime. So that's on our way out. This is our time from x to y, and this is our time on the way back from y to z. So in this case, going from x to y, we've got our starting length, L, and then we've got that little bit extra because y is moving away from where we started. So we've got this v delta t1 prime. Now on the way back, we've got our y to z, and that then is going to be the starting length minus v delta t2 prime, because z is going to be moving towards the mirror on the way back, so we need to take off that difference. But we could also add to these our calculation using the speed of light. So our xy here, the time to go from x to y, because we've got our delta t1 prime here for the time, well, we can say that that is going to be our velocity multiplied by the time. So delta t1 prime. We can say a similar thing for the path from y to z. So we can say that is delta t2 prime multiplied by the speed of light. So we've now got a couple of equations. So all we need to do, as we did on the previous video for the previous slide, for the time dilation, combine these three equations and we get ourselves a length contraction formula. So let's isolate delta t1 prime and delta t2 prime in these two equations then. So delta t1 prime is then going to be L divided by C minus V. And then delta t2 prime is going to be L divided by C plus V. And we know if we add these two together, we get delta t prime. So we want to add those two together to say delta t prime is going to be, well, a combination of the two of them. We did exactly this combination in the Michelson-Morley experiment calculations. So we end up having 2cl divided by c squared minus v squared. That's just adding these two fractions here together, getting them over a common denominator. So pretty straightforward there. Now we do know with this, because we've already derived the time dilation formula, that we can say, well, this is going to be our proper time here, because this is our frame of reference is at rest with respect to the source. So we can say that our delta t prime is equal to delta t divided by the square root of 1 minus v squared over c squared. So this is going to help matters as well, because we're now going to be able to eliminate these delta t's and delta t primes and things. So let's stick with this equation that we've got here, because we can replace that delta t at the top with a 2L0 divided by c, just putting this equation in there. And then we can bring in this one, and then we've got rid of delta t prime as well. So we'll have 2CL divided by c squared minus v squared is going to be 2L0 over c square root of 1 minus v squared over c squared. So now we just need to do some rearranging just to make L the subject. So get rid of the 2's, and then we've got that c, we can make that a c squared. Get rid of that c squared over c squared, c squared minus v squared, multiply both sides by that. So now we've got L as our subject. Now, this doesn't look exactly at the moment like our time dilation formula. We have to do a little bit more manipulation. So let's deal with this. Let's get rid of that c squared there to divide that c squared and leave a 1, and divide that v squared to leave a c squared. So what we've got, just to make that look neater, is L0 multiplied by 1 minus v squared over c squared divided by the square root of 1 minus v squared over c squared. So now you can see when we divide the numerator by the denominator, we're just left with L0, the square root of 1 minus v squared over c squared. So this is a more complicated derivation, I would say, than the time dilation one, but it's still, not exactly off the charts in how complicated it is. The main thing which seems weird, I suppose, with these derivations is, and we had the same thing in the time dilation one. When we're looking at this length contraction here, so we've set off saying, right, in this frame of reference, we've got this distance here from A to B that's L0. This is our proper length. When we start in the, even from the starting point of our moving frame of reference, our f prime, then the distance from x to the initial point, so where B is initially, so we could have them exactly the same coordinates. This could be overlapping, as in the origin of f could be exactly the same as the origin of f prime, in which case when the pulse is first emitted, A and B will be in the same locations in both frames of reference, but we're not setting the distances to be the same. This is the point of the fact that we've got a length contraction, because frame of reference f prime is moving relative to the point A. So we have to set that to be L, not L0. So that's why we have to have an L here and an L here. We don't have an L0 because we're trying to show the length contraction. We're trying to show there is length contraction because we're still measuring the same C in both frames of reference. So C isn't changing, L is changing. This is the difference really from what we had before when we were doing transformations. If we were doing Galilean transformations, we would have changed this C and said, okay, well, we need to modify C according to V, the velocity of the frame, and then we do our transformation. Now in special relativity, we're not saying that. We're saying, right, C is the same. It's L that's changed. That's what's giving us this formula, because we're getting this change in the measured length, depending on what frame of reference we're in. So that's the bit which is different, which is new, really, when we're making this derivation. Right, so I got a little bit of time. I'm not going to do much in the way of questions here. I'll do a couple just to make a few points, I suppose, because it's always nice to do more questions on special relativity, even if they're really simple ones, just to remind ourselves of what's going on. So we'll do a quick time dilation one then. So you've got a spaceship passing at 80% of the speed of light. Our favourite speed sets out a flash of 2 microseconds. So this is in the frame of reference of the ship. So on the spaceship, that is how long the time is measured for. So that is our T0. That's our proper time, because the flash, the source of the flash, is at rest in the frame of reference of the ship. So it's our proper time. If you were on Earth looking at this ship go past, Then we do our square root of 1 minus v squared over c squared, which using 0.8c for v then gives us 0.6. So the time that we're going to measure on Earth will be our t0, our 2 microseconds, divided by 0.6, so multiplied by 5/3. So we're going to get 10/3 microseconds. That is the time recorded by a clock in the frame of reference of the Earth, having that as its rest frame. So that's what we've got with time dilation. You can do other calculations with the time dilation formula as well. You don't, if we've got this t equals t0 divided by that square root of 1 minus v squared over c squared. Okay, you can do calculations for t and t0, but we could also work out v. So if we were going back to muons again and said, right, the muon at rest has got this 2.2 times 10 to the minus 6 seconds. So that's at rest. That's the lifetime of a muon, say, when it's at rest. If it's at high speed, so say we measure a lifetime of 6.4 times 10 to the minus 6 seconds. If we've measured that as a lifetime, so that will be our t, that will be our t0. So what are we then going to get for v? So we're just putting those numbers in, and then we're solving that for v, which is trivial to do. Ends up coming out at like 94% of the speed of light. I don't really need to step through the numbers on that. So just stick it in the calculator and you'll get your answer. And we can also see how this ends up being a valid approximation if you're not moving at particularly high speeds. Say we took 300 meters per second. Say we had an aeroplane rather than a spaceship, and 300 meters per second. Okay, that's a fast aeroplane. Okay, it's not that no aeroplanes go that quickly. We're getting up near the speed of sound there, but it's maybe a little bit faster than your average commercial plane, but not far off. But it makes it easy. We got 3 times 10 to the 2. Compare that to our 3 times 10 to the 8 for the speed of light. So when we square both of these and we do this fraction here, then we're going to have a difference of 10 to the minus 12 there. So we've got 1 minus 10 to the minus 12, which we then need to square root. Now your calculator is not going to be able to handle that unless you've got a particularly fancy calculator. So you'd have to go for binomial expansion, do a 1 minus v squared over c squared to the minus a half. And if this is a really small term, which it is, 10 to the minus 12, then we're going to get roughly equal to 1 plus nx. So the minuses are going to cancel out. So you'll have v squared over 2c squared. So for this particular case, this is going to be roughly equal to what we're going to have. We're just going to have, well, plus 10 to the minus 12 over 2. So that's not a very big difference by the time we factored that in. So 1 plus 10 to the minus 12 over 2. That is a small percentage change. So if we were going back to that 2 microsecond pulse, then by the time you've just added on, well, that's going to be 10 to the minus 18 is going to be the change. So you've got 2 microseconds plus 10 to the minus 18 seconds by the time we put that Lorentz factor onto the measured time. So not really noticeable. You can see why this is then just a good approximation of saying, well, we've got a universal time. If you're not moving that quickly, there isn't really much of an effect of time dilation. I'll do a quick length contraction one then. So say you've got a 60-meter spaceship. So that's going to be our L0 as measured in the rest frame of the spaceship. How fast, if it's moving at, let's go for an actual calculation. So it's moving at 98% of the speed of light. So what length is going to be measured? Now this one is different. You have to be more specific when you're saying what length is going to be measured if you were in a frame of reference moving at a relative speed of 98% of the speed of light, because you need to say what direction is moving in. We didn't have that issue with time dilation. You just do the time dilation. Here, if that 60 meters is going to change, it needs to be moving in the direction of the 60 meters. So if you've got a spaceship which is 60 meters long, okay, this length contraction is going to happen if it's moving along that length. If it's moving that way, the contraction is going to be in the width rather than the length. So you do need to specify that. But otherwise, we're saying, right, well, the measured length, if you were on Earth and this spaceship was flying past, you'd say it was our 60 meters, and then you multiply by 1 minus the square root of v squared over c squared. In this case, we're getting 98% of the speed of light we're putting in here for v. So it comes out at 11.9, give or take, meters. So that's a big length contraction. But you need to be careful when you're doing length contractions that you're getting the length that's in the direction of the relative motion. So again, fairly simple calculations. I'll get on to slightly more complicated calculations in other videos at the end of this block. This video I think has gone on long enough. There's quite a lot packed into this one. But at least we've got more depth now. We've got more substance to our calculations because we know where these formulae are coming from, which is always a useful thing when we're doing calculations like this.